we saw there the actual Michael reaction itself requires a stabilized enolate. Well, what if we don't have a stabilized enolate? What if we just have something like cyclohexanone, and I want to do reaction at the alpha carbon to that? Well, we have a little trick we can do that can make cyclohexanone or just some regular ketone like this into a very stable enolate. What we do is think back to our ketone aldehyde chapter and think about what happens when we react a carbonyl compound with a secondary amine. That's a nitrogen compound with two R groups on it and an H. You can look back at this mechanism if you like, but what typically will happen is the carbonyl is protonated first, the nitrogen adds to it, there are proton transfers, and we end up losing water. Okay? So we end up with an imine, but then to get it neutral, we have to eliminate hydrogen next to it. So this is an enamine. In order to get everything to fit properly, it has to look like this. Otherwise, we'd be trying to add an H to what was originally the carbonyl carbon. Okay? So an enamine, remember, is sort of like an enol. Right? It's a CC double bond, and attached to that is an N with its two original R groups. So a very common secondary amine used to make enamines is pyrrolidine. That's a 5-membered ring, so it's like cyclopentane, but it has an NH in it. So it's NH and then 4 CH2 groups in that 5-membered ring. So that's pyrrolidine. That's a very common compound used to make enamines. So cyclohexanone and pyrrolidine makes this cyclohexene, where I have a double bond in this ring, and then attached to one of those double bonded carbons is the 5-membered nitrogen ring. So look at how an enamine looks very similar to an enolate ion. Right? An enolate has C double bond C and O minus attached. An enamine has C double bond C and NR2 attached. In both cases, electrons from the heteroatom can come down, making a double bond, and that pushes electron density onto the alpha carbon in both cases. So in the enolate, that's why we have a nucleophilic alpha carbon, because one resonance structure has C minus on the alpha carbon. In an enamine, if I push electrons down, I can get a resonance structure with a C minus on the alpha carbon. I just happen to also have an N plus now over there. But N plus is a little more stabilized than some other things. So an enamine is essentially a way to have a stable neutral molecule that reacts much in the same way that a enolate would. So if I have an enamine, let's make cyclohexanone. Actually, let's put a methyl group on one of the alpha carbons just for fun here. If I react that with pyrrolidine, so I'm going to draw a 5-membered ring. I'm going to put an N in one of the positions and an H on that end. So that makes the enamine. And what's interesting is that the double bond that forms goes to the less substituted position. It's actually very similar to what LDA would do to make a regular enolate. Okay? It goes to the one that has more room on it. Okay? Not necessarily the more stable double bond, which would be the more substituted one. It actually goes to the one that has less substitution to it. So I have this enamine. So if I react that enamine with some type of electrophile, what can happen is the lone pair from the nitrogen comes down to the carbon, and then that causes the CC double bond pi electrons to go attacking the electrophile. And what we end up with immediately after that anyway is an iminium ion, right? That's a double bonded N with a plus, and our electrophile added to the alpha position. Then water will hydrolyze that iminium ion, sort of the reverse of the enamine formation, giving us back the original carbonyl that we had, but now an electrophile has been added to the alpha position. Okay? So what this is just a very nice, neat, tidy way to add an electrophile to the alpha position of just a regular monoketone. This is necessary in the Michael reaction, remember, because I said the Michael reaction requires a stabilized enolate. Just making cyclohexanone into an enolate with LDA, that's too reactive of an enolate to properly do a conjugate addition. Okay? It'll actually just do a regular 1,2 addition, and there will be other weird things that happen too. So won't be nearly as interesting to us. So to get a good clean reaction with just a regular ketone, we have to make the enamine first. Okay? Then the electrophile adds the alpha, and then water just replaces our carbonyl for us. So here's that same mechanism, just like we drew. It actually shows one more intermediate here. Look what happened. Right here is the enamine, and in the actual reaction where we can react it with a alpha beta unsaturated compound like this, right? The enamine adds to the beta carbon of the enone here, and that behaves just like the Michael reaction from then. So here was alpha and beta, right? When the enamine nucleophile adds to the beta, that pushes electrons onto alpha right there. So now my immediate product of this is an N plus, where the enamine was, and a minus here at the alpha carbon. So just a simple proton transfer will make a neutral molecule. We'll regenerate an enamine. That way, it'll actually take one of these H's off. Right. But then water adds, it regenerates our carbonyl compound with H back on the alpha again, where it belongs. So don't get too caught up in a lot of this business here. Keep yourself grounded in what we've accomplished here. We had a ketone. To make a stabilized nucleophile out of it, I made an enamine, right, which has a CC double bond in here with the N attached. The alpha carbon of the enamine attacks the beta carbon of the enone in a 1,4 addition. So, in our product here, right here is the new carbon-carbon bond that was formed. And we do proton transfer that regenerates the neutral enamine, but then water hydrolyzes that enamine in essentially the reverse of the enamine formation over here. Regenerates the original ketone we had, but the difference now is that we have something attached to the alpha carbon. And our direct product of this is just a plain old 1,5 diketone. No temporary ester groups or anything, nothing else attached to that alpha carbon. Okay? So if you see a product that is a 1,5 diketone, probably the most efficient way of doing that is with a enamine, right? It's called the Stork reaction. So the retrosynthetic disconnection happened between carbon 2 and carbon 3. So that's because the alpha carbon of essentially the enolate added to the beta of the enone. That way. So there are clear advantages to using an enamine instead of an enolate, because enamines are stable and neutral. Okay? You can prepare this enamine and you can put it in a vial and save it till tomorrow when you do the reaction, for instance. When you make an enolate, there's no turning back. It's only good for a matter of minutes, if that, and once you form the enolate, you have to react it immediately. again, we can start with just a monocarbonyl compound, just a regular plain old ketone as our nucleophile. The normal Michael reaction requires a stabilized beta dicarbonyl, so something with two carbonyls and a stabilized minus in between them. We can, however, make that same product using the standard Michael reaction, but we would have to decarboxylate the product, and it's a little more work. Here's the same product that we made up above. Let's deconstruct it retrosynthetically. So 1, 2, 3, 4, 5. If I want to think about making this, and if I wanted to do this with a regular Michael reaction, what would have to happen here is that on the alpha carbon to the carbonyl that's the nucleophile, that would have to have a temporary ester group attached. So CO2ET, because then the bond that could have formed, we could have had this alpha carbon be a stabilized enolate. And this over here could have been our enone. Right. So that's a retrosynthetic deconstruction. To go in the forward direction, what we would have to do is take this beta keto ester, deprotonate it, ethoxide, react it with the enone, to do the Michael reaction, right? Alpha adds there. My ester group there. Right, let's just track our carbons here. Alpha and beta of the enone becomes alpha and beta there to the second carbonyl. And then if we use hydronium and heat, we can decarboxylate. You can remove that temporary ester group. So it's a little more, well, I guess it's probably the same amount of work, but it's a little tougher to see retrosynthetically, because if this is your product, you have to imagine this ester group sort of appearing there. Whereas if we have a 1,5-dicarbonyl, we can very easily imagine that we just break the 2,3 bond and have a enamine, like this one, that could have done the reaction.